Alright guys, welcome to another class. Today we'll be talking on waves. This is a very important topic and it's going to be tested so well in your exams. So without further ado, let's get straight into, waves. Basically, I believe, you should understand what waves are. And, but in case you don't understand, let me just give you a quick introduction into wave. Basically, a wave is a disturbance in a medium that causes energy to flow from one point to another point. So it's a disturbance in a medium that transfers energy, basically. And if you could understand this, you understand what a wave is. So when you have a disturbance in a particular medium and this disturbance is capable of transferring energy, moving energy from one point to another point, that is a wave. Basically, wave have some basic characteristics. Let me try and illustrate what a wave is going to look like. I imagine this is a wave. Basically, let me use the word waves. They have some basic characteristics. And what is the characteristics? Let me illustrate this for you. I'm coming. Now imagine this is a wave. Or this is a depiction of a wave. What are some of the important characteristics of this wave? The first thing we have to talk about is the amplitude. And what is the amplitude of the wave? The amplitude of the wave is basically the maximum displacement of the particles of a wave from the equilibrium position. It means what is the maximum height or depth away from the equilibrium point of this wave. And basically, if we could show you what the amplitude is, let me show you in white. This is the amplitude. Look at it. This is the maximum displacement. This is also the amplitude. This is the amplitude. Like that, so this is also the amplitude. Why? This is the maximum displacement of the particles from the equilibrium position of the wave. The green line represents the equilibrium position of the wave. So we've talked about amplitude, and basically we can use the symbol A to represent amplitude. This is usually measured in meters, so that's not going to be a problem. The next thing we need to talk about is something called a wavelength. Lambda. To understand wavelength, we have to understand a new concept that allows us to fully grasp wavelength. And what is the concept that allows us to understand what wavelength is? The identification of something called crests and another point called trough. So look at it. The maximum point up on the top of the wave, the maximum point at the top of the wave is called the crest, while the minimum point at the bottom of the wave is called the trough. Are we together? Crest. The middle is called equilibrium position. Equilibrium. So this place is called. Now, what is a wavelength? A wavelength is the distance between two successive crests or two successive troughs. Okay, let me do it in an ink that you should be able to see. That green is hiding. So this is a wavelength, one wavelength. I could also call this one wavelength as well. This, I could also call this one wavelength. You understand? So this is a wavelength. This is also a wavelength. If I pick two successive crests or two successive trough, then I have a wavelength. The word successive means they follow each other. It could be two equilibrium points with one crest and one trough. Then let me do this in white. Look at it. Imagine I start from this particular point here on the wave, one trough, one crest, back to the equilibrium point. This is another wavelength. That particular distance is also another wavelength. Let me try and illustrate it for you. Sorry, my pen is just misbehaving a little. So this is another wavelength too. So I could say it's the difference or the distance between two successive crests or two successive trough or two equilibrium points containing one crest and one trough. And basically, wavelength is still also measured in meters. So they are both measured in meters. Then we have something else called time or period. And what is a period? A period is the amount of time that it takes to complete one cycle of a wave. What is one cycle of a wave? One cycle of a wave is from the equilibrium point to the crest, back to the equilibrium point, then to the trough, and back to the equilibrium point. This is one cycle of a wave. This is one cycle of a wave. So the amount of time it takes the wave to complete one cycle is the period. Does that make sense? So we could basically say period is the number of seconds it takes to complete one cycle. And this is going to be measured in time or in seconds, any how you want to put it. So period is usually measured in seconds, or you could also see period as the number of seconds it takes to complete one cycle of the wave. Then we have something else we need to talk about, something called frequency. Well, frequency is basically the reciprocal of your period. Why do we call it reciprocal? Frequency refers to the number of cycles that can happen in 1 second. So, how many cycles of a wave can I have in 1 second? That is frequency. Altogether, most times waves will be measured in frequency altogether. And if you look at frequency and period, you would notice that if I do 1 over frequency, I'm going to be getting period. At the same time too, if I do 1 over period, I'm going to be getting the word frequency, which means there is an inverse or reciprocal relationship between period and frequency. Simply put, frequency is measured in hertz, kilohertz, megahertz, gigahertz, and the likes. Yeah. That's basically I think something else we need to talk about is the speed or the velocity of the wave. What can we use to calculate the velocity of the wave? Basically, we could just use one simple formula. We can recall that velocity is equals to distance over what? Time. Isn't it? or you can say displacement over time, any you want to call it. And the displacement of one cycle of a wave is the wavelength, and the time is basically the period. So we can say the velocity of a wave is equals to the wavelength lambda divided by the period time. Does that make sense? Yeah, so it's the period over time. And we can establish a relationship from here that V is equals to lambda over T, or V is equals to lambda over, we recall that T is equals to 1 over F, so I could say T over 1 over F, which becomes lambda times F over 1, which is equals to lambda F. Therefore, simply put, anyone you want to take, therefore simply put. So simply put, we could say V is equals to lambda over T or lambda F. These two, you have to remember this relationship very well, because you'll be using it later on when you are working on waves. I would advise you just write this relationship down. V is equals to lambda over T or lambda F, and T is equals to 1 over F, or F is equals to what? 1 over T. Alright, let's just solve a basic question, then we go on to something more advanced or something more important. Okay, let's see if you could solve two questions. They said, let me see if I could import the picture. Okay. Let me see if I can import the picture to my OneNote. Insert pictures from file. Alright. Let me try and expand the picture so you guys can see it clearly. Now, they said the diagram below shows a part of a wave motion in air. They said if this wave travels with a speed of 300 meters per second, calculate the frequency. Yeah, what was given to us? We are given the velocity of the wave to be 300 meters per second. Now, if we are told to find the frequency, there's a relationship between frequency and velocity. Remember, I said V is equals to lambda F. Are we together? This is the relationship between velocity and frequency. Now, there is wavelength too. Look at it. We are told that the distance between point O here and this point is 3 meters. The entire length is 3 meters. The question is, how many wavelengths do we have in this length? Look at it. Let's go together. This is one wavelength. One. This is two wavelengths. And this is half wavelength. So basically, we have 2.5 wavelength. Or we can see we have 5 over 2 lambda. Now, if we establish the relationship that 5 over 2 lambda is equals to 3 meters, I hope you understand this relationship. If 2.5 wavelengths is equals to 3 meters, yeah, then we can find lambda. What is the value of one wavelength? We're going to be having 5 lambda is equals to 6. Then you could divide both sides by 5. I'm going to be having lambda is equals to 6 over 5 meters. Does this make sense? So this is my wavelength. And now I could find the frequency. From here, frequency is going to be equals to V over lambda, which means 300 divided by 6 over 5, which is something I'm saying 300 times 5 over 6. 6 here 1. Can 6 go in 300? Yes. 50. 50 times 5 is what? 250. So it's going to be 250 hertz. Quite excellently done. It was simple, not too difficult. But I hope you understand. If you do not understand, try to replay the video for as many as possible times. Okay, I would also try to speak more slowly for those of you that have problem with the speed of my words. I'll see if that would help a bit. Now let's try and solve a harder example. Let me see if I have a very hard example here. Let me see if I have a very hard example here. Okay, I think I have maybe a more difficult example. Maybe. And let me import it. Yeah, let's import the new picture. Pictures from file. All right, I'm going to be solving on the side. I said the figure represents a displacement time graph of a traveling wave. So this is a displacement time graph. What were we given first? We are given the velocity of the wave to be 2 meters per second. That's not all. We are given the amplitude to be 0.2. Is this in meters? I guess. Oh, there's a solution there. So we've been given the amplitude to be 0.2 meters. What else were we told to find? So they said we should determine the amplitude. Well, that's what am I writing? We've gotten the amplitude already. That's easy. The amplitude is 0.2 meters. Look at it, the distance from the equilibrium point to either the crest or to the trough, which is still the same thing. 0.2 meters. Yeah, what's the next thing? I said we should find the period. Now we have the entire graph. Okay, look at it. One wavelength is 0.1. Oh, this is time. This is time. Now the time it takes to complete one wavelength, look at it. The time it takes to complete one wavelength is 0.1 seconds. This is time. Please don't mistake this for meters. This is time. So the time it takes to complete one wavelength is 0.1 seconds. Therefore, that is the period. 0.1 seconds. Does that make sense? What else are we also told to find? We are told to find the wavelength of the wave. Is there any relationship between wavelength, velocity, and time? Yes. There's a very simple relationship. We know that V is equals to lambda over T. That relationship I told you to write down. Check it. V is equals to lambda over T. Therefore, you could say that lambda is going to be equal to Vt by cross multiplication. And therefore, our wavelength, which is lambda, is going to be equal to 0.1 second multiplied by 2 meters per second, which is going to be equal to 0.2 meters. That is our wavelength. I think that should suffice for now. Let's see if you could do something more advanced for waves. Alright, let's talk about standing waves or stationary waves real quick. Standing/stationary waves. They are the same thing. What is a standing wave or what is a stationary wave? I'd like to illustrate this visually, but I'll still explain with words anyway. Now, if I have two progressive waves that move in opposite direction to each other, having the same amplitude and the same wavelength, then both of them form one standing wave. Let me explain that to you with the diagram. Imagine this is one wave, and this is another wave moving in opposite direction. Look at it. We have two waves. The first wave in white, the second wave in green. Two waves of the same amplitude and they're moving in opposite direction. The same wavelength. Both of them together forms a standing wave or a stationary wave. Is that clear? Now, there are things you need to know about stationary waves or standing waves. 1. Nodes. 2. Antinode. I have written here, I said a node is a point whereby there is no movement in the wave. I'll illustrate it. And where the point where there are no movements in the waves, they are on the equilibrium point. So this is a node. This is a node. This is a node. There are no movements there. It's on the equilibrium point. This is a node. This is a node. And this is another node. There are no movements on this part of the wave. It's on the equilibrium point. What about an antinode? An antinode is a particular point whereby there is maximum movement in the wave. And where are the antinodes? I could say this is an antinode. I could put it up, I could put it down. They mean the same thing. So this is one antinode. 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 I'm having the maximum displacement here, the maximum movement in the wave. So the antinode occurs at the amplitude, while the node occurs at the equilibrium point. Alright. If you notice from the diagram, the difference between two nodes, that is, if a wave has only two nodes, how many wavelengths does it have? This is a complete wavelength. Let me do it in a different color. See, this is a complete wavelength from here down to this place. But if it has only two nodes, it means it has done only half of a wavelength. Are we together? So I'm going to say 2 nodes, half of a wavelength. 3 nodes, 1, 2, 3, 1 wavelength. 4 nodes, 1, 2, 3, 4. Look at it. 1, 2, 3, 4. This is 1.5 wavelengths. 1.5 is 3 over 2. 3 over 2 lambda. 5 nodes. That's 2 wavelengths. Let's do 1, 2, 3, 4, 5. If you trace it, this is 1 wavelength. This is another wavelength here. So that's 2 wavelengths. If you notice, there is a relationship between, the nodes and the amount of wavelengths. I could say xn is going to be equals to, what's this? X minus 1 lambda over 2. It's a quite confusing relationship, but you'd understand it. X could be any number. X node. Imagine a wave has 7 nodes. Then how many wavelengths does it have? It's going to be having 7 minus 1 wavelength, which is going to be 6 wavelengths over 2, which is going to be what? 3 wavelengths. So it's a very, very intuitive way to calculate the amount of wavelengths, just by knowing the nodes in the particular standing wave. So let's say the standing wave has, let's say, 26 nodes. How many wavelengths are in this particular wave? We could just use the formula x nodes is going to be equals to x minus 1 lambda over 2, which is going to be 26 nodes would have 25 over 2 wavelengths. 25 over 2 is 12 and a half, so that's 12 and a half wavelengths. Does that make sense? All right. We've talked about nodes. Let's talk about antinodes or antinodes. These are antinodes, like I've illustrated before. Now, if a graph has one antinode, just one antinode, it has one antinode, it means there's only half of the wavelength in the graph. Look at it. This is only half of a wavelength. So we can start writing the relationship somewhere. One antinode, half of a wavelength. 2 antinodes. How many wavelengths do we have? 1 antinode, 1 antinode, 2. So we have 1. So we have 1 complete wavelength. See the wavelength. Are you seeing it? This is 1 complete wavelength. That's 1 complete wavelength. That's lambda. My bad. Three antinodes. We have, look at it, antinode 1, antinode 2, antinode 3. So if you trace it, we have wavelength 1, then half. So we have 1.5 wavelength. That's 3 over 2. If we have 4 antinodes, so basically you should know it's going to be 4 over 2 wavelengths. Let's look at it. 1 wavelength. That's 2 antinodes. Here and here. Another 2 antinodes. Here and here. So when we have 4 antinodes, we have 2 wavelengths. And we can keep going. 5 antinodes. 2.5 wavelengths, which is going to be 5 over 2 wavelengths. Which means there's a relationship between the number of antinodes and the wavelengths. So we can say x antinodes altogether is going to be equals to x lambda over 2. Easy. So for antinode, let me delete this. For antinodes, we are not going to be minusing 1, but for nodes, we are going to be minusing 1. So let me write both of this relationship in white. X node is going to be equals to x minus 1 lambda over 2. While x antinode is going to be equals to x lambda over 2. This is the very, very important relationship that you have to remember. Let's take some questions on this. Let me try and insert the question. Where's my sniping tool? Yeah. Please, in case you don't understand what we've just done, you could replay the video for as many as possible times as you want, or you could just keep one video till you understand it. Is that clear? Yeah. Let's take an example right now. Why do I still have this? I thought I deleted it already. Delete. Please, before we even put the example, make sure you write this down in your book. This relationship here that we have. See this relationship. Make sure you write that down. This relationship. Make sure you write it down. Alright. You can go on. Let's drop the example. And I said a wave of frequency 10 hertz. So they've given us the frequency in the question. They say frequency is equals to 10 hertz. Forms a stationary wave pattern in a medium where the velocity is 20 centimeter per second. They said the distance between the adjacent node is, that is what the distance between one node and the other node. So the distance between a node and the node that follows it. What they're asking you is, imagine you have a standing wave that looks like this. What's the distance between node 1 and node 2? It's very, very easy. Basically, you know that the distance between two successive nodes, that's, just remember, once a wavelength has two nodes, you can come back up. If it has two nodes, then it has half of a wavelength. Therefore, the distance between two nodes is equals to lambda over 2. But now, we need our answer in centimeter. We need our answer in centimeter. So let's first come back between, what's the relationship between V, lambda, and F? We have an equation that says V is equals to lambda F. Are we together? So what is our V? We have our V to be 20 centimeter per second is equals to lambda F. And what is our F? 10 hertz. I always like converting all my meters to, I always like converting all my centimeters to meters, sorry. It makes my calculation easy. So 20 centimeter is 0.2 meters. So 0.2 meters per second, 0.2 meters per second is going to be equals to V lambda multiplied by 10. Are we together? It is always very, very important to convert your centimeters per second to meters per second. Do not do that mistake of not converting. So to make lambda stand alone, I'm going to be having 0.2 meters per second divided by 10 hertz. 0.2 divided by 10. If you punch your calculator, let me see if I can pull up a calculator right now. Calculator. Okay, I've pulled up my calculator. So I'm going to be having 0.2 divided by 10. And I got 0.02 meters. 0.02 meters. Now I have to just convert my answer from meter to centimeter. From meter to centimeter, you multiply by 100. Therefore, this is something as saying 2 centimeter. Option C. Very easy. Let's see if you could solve another question very fast. Yeah, let me snipe and insert. All right. All right, I should be able to insert the picture now. Insert pictures from file. Yeah, this is another example that we need to solve right now. Okay, the question says radio waves emitted from an antenna are picked up by radar after reflection from an aircraft in 4 times 10 raised to the power 10 minus 3 seconds. So they've given us time or period. We have time to be 4 times 10 raised to the power negative 3 seconds. And we have the velocity to be 3 times 10 to the power of 3 meter per second. They are asking us to find the distance between the aircraft and the antenna. This is a very, very easy question. You just have to use the basic relationship that you know. Distance, let me just call it, displacement. I know that displacement is equals to velocity times time. Therefore, I could say the distance is equals to 3 times 10 cube times 4 times 10 to the negative 3 seconds. This cancels this. 3 times 4 is 12 meters. Okay, now, there's something important you have to pay attention to. They said the waves were picked up after reflection. Reflection means it has traveled, bounced off an object, then it bounces back. So it has done 1 distance, 2 distance. Are we together? Let me call the distance wavelength just for this example. It means the distance covered by this wave is 2 wavelengths. Are we together? So if the distance covered is 2 wavelengths, it means it did 1 wavelength in half of this second. Are we together? It did 1 wavelength in half of this second. Therefore, I could say the time for 1 wavelength is going to be equals to 1 over 2 times 4 times 10 raised to the power negative 3 seconds, which is going to be 2 times 10 raised to the power negative 3 seconds. Now I have my time to complete, 1 wavelength to know the distance. How far is the aircraft from the antenna? So my time is 2 times 10 raised to the power minus 3 seconds, and my velocity is 3 times 10 raised to the power 3 meters per second. What am I going to do now? I'm just going to do velocity times time. Sorry, this is A. This is A. The question had issues, so let me change my velocity. It is 8, not 3. I'm just checking it from the hard copy. This is 8. This is 8 too. Now, if the velocity is 3 times 10 raised to the power 8 and time is this, therefore my distance is going to be VC. For some of you that are still confused, let's say this is the antenna and this is the aircraft. Now look at it. The radio wave went this distance, then reflected back to the airplane. Are we together? So look at it. The distance between the antenna, which is this, and the airplane is just one of these wavelengths, not both of them. Although the time it took the wave to travel is this wavelength there and back. So we did 2 of this journey in 4 seconds. Are we together? Therefore, the distance, the time to do from here to here is just half. That's 1 over 2 times 4 times 10 raised to the power minus 8 seconds. This is minus 8, that will be minus 3. This is minus 3. Do you understand it? He did this journey and back in 4 times 10 raised to the power minus 3 seconds. But the distance between the antenna and the carrier is only half of the wavelength. Therefore, the time we are going to be using here will be the time to move from here to this particular point. That's why I say time lambda is going to be equals to half times 4 times 10 raised to the power minus 3, which give me 2 times 10 raised to the power minus 3. So we could go on and divide. We could go on and divide. And if we go on and divide, what are we going to be having? Or is it divide? We are multiplying, my bad. So the distance is going to be equals to 2 times 10 raised to the power minus 3 times 3 times 10 raised to the power 8. Yeah, I'm going to be having 2 times 3 to give me 6. And minus 3 plus 8 is going to be 5. So I have 6 times 10 raised to the power 5, which gives me 6,000